Okay. Are we ready? Okay. So remember, calculus addresses two problems. The one problem was, how do I find the slope of a tangent line to a curve? And we spent like months working on that. Lots of applications too. Now we're looking at area under a curve. Okay, so today we're going to look at a different way to figure out the area. And you will like this better probably than the infinite sum of rectangles. Although this is also an infinite sum, as we talked about last week. As you look at this trapezoid at the side, the formula for the area of that trapezoid would be area is equal to 1/2 a plus b. So the two parallel sides, a plus b, times 1/h. No, just times h. What am I doing? I don't know. Let's just bring this there times h. Good? All right. Close up your notes. Because I want your full attention, not distracted, writing things down. I'll give you time. I'll give you time.
No, maybe not.
Okay. Close your notes.
I'll close it for you, man.
Shh. Hey, close your notes. All right. Well, let's just suppose I want to find the area between a and x under this curve. Okay. Now, what that area is kind of depends on how far to the left, to the right, this x is. Right? So the bigger my x is, the bigger my area will be. So in some way, I don't know how, this area depends on x. Right? So let's just say that, oh, this area is a function of x. Good? Yeah. So now let's imagine I extend going from a to x plus h. What would that area function be? A of x plus h. There we go. A of x plus h is that whole thing. Oh yeah, look at that. Now, why, for fun, suppose I wanted to find this area in between x and x plus h. What would I do? Area of x plus h minus the area of x. So I could just subtract those two. And I'm going to call that the change in area. Okay? All right. We'll come back to this diagram as we go. We're just setting the stage here. You ready? Sharia. Do you have a question, Sharia? Okay. What's that hoodie doing here? Get rid of your hoodies. Put them away. All right. So this is what we decided. If I do area of x plus h minus area of x, that's going to give me that change in area. Good. Now, suppose I divided each of these by h. Is that legal math? Seems to be legal. Ooh, and what if I did a limit as h approaches 0? What's the definition of the derivative? This thing here is the definition of the derivative. So this would be the derivative of what? Derivative of the a function. So A prime of x would be the limit of that change in area over h. As h goes to 0, so if we come back here, as this h goes to 0, what happens to this area? Gets smaller, also goes to 0. Okay, so I'm going to get a 0 over 0. Who knows what's happening there? Yep.
Wait, so why did you divide by h?
So that I could get this this to be the definition of the derivative. I wanted to get to that point. Good? All right. So now let's say, well, the area, that delta A, that's approximately this trapezoid area. Is it a good approximation? No. It's not great. It's better than a rectangle. Still, yeah, bad. Okay. So that was the formula for the trapezoid area, where earlier we said this would be A and that would be B, and this is H, that width there. Good? Now, if you remember what we had over here, delta A of x over h, what if I just divided both of these by h? Does that show up next? Oh, maybe before I get to that. Sorry, I'm ahead of myself. The A is f of x, right? So this A height here, this height, since this is x, this height is f of x, right? And this height over here is going to be f of x plus h. True? Okay, so that's all I did. I just did a substitution, replaced the A with f of x, B with f of x plus h. Good? Don't be distracting. Yeah, keep your feet to yourself. Suppose, as I mentioned earlier, I divide this by h. And I divide this by h. So then we're still not there. These h's are going to cancel out, just like this h and this h will cancel out. And there, I have this over h. What do I want to do to both sides? The limit, because I want to come up with this. So if I do limit as h approaches 0. Okay, so what do I have? So far, I know my derivative of my area function is equal to this limit, which is equal to this limit. Okay. So here we go. And I keep sticking those h's in. That should just be canceling out already. Hey, if those h's cancel out, then what happens as h goes to 0? F of x plus f of x, which is 2f of x times a half, is f of x. So if this cancels out, what is the derivative of my area function? It's the curve. So the derivative of my area function is the curve that's at the top of the function, at the top of that area. Gobin. We're just going to use the idea. This is just to convince ourselves why it's true. Yep.
Is this exact or is this?
It's exact, right? So notice at this point, okay, here my change in area was approximately the trapezoid area. But notice here, once I did the limit, as h goes to 0, both of them go to 0. It's exactly the area. So now we have equal signs. It's exactly equal to. All right. Do you want to write any of this down? Let's get this going. The curve function f of x is the derivative of the function representing the area under the curve. Okay, so this is just restating what we did on the previous page. If the function is the derivative of the area underneath it, then we could say the area is not the derivative. How do we undo derivatives? The antiderivative, or indefinite integral, of the area underneath. So today, we're going to use the antiderivative to find areas under curves. Okay. Here's what we'll do. Looking at this example, I want to know the area under this curve above the x-axis from 1 to 2. So I'm looking at from 1 to 2, what is the area of that section there? Here's where I start. I'm going to say A of x is going to represent the area under the curve from 1 to x. If that's true, A of 1 equals 0. So you'll remember from Friday, we did antiderivatives. With antiderivatives, indefinite integrals, we always did a plus c at the end because we didn't know the vertical position of that graph. But if we had 1 point on the graph, we would know the vertical position. This is giving us 1 point. So we can find an exact equation for the function. So my area function will be the integral of 4 minus x squared dx. Rayon? Yeah, so another way to look at this area here is that instead of adding a layer at the top, I could imagine I'm adding a layer on the edge here. And if I imagine that this is a rectangle, it'd be infinitesimally thin, so basically the width will be 0. The width of that is dx, and the height of that is f of x. So I have the height of f of x times the width dx, and I'm doing an infinite sum of rectangles. So again, that long s integral symbol means it's an infinite sum. Mahi, you had a question? Sorry, say that once more. Well, if A of x is the area under the curve from 1 to x. If I'm going from 1 to 1, there's no area because there's no thickness to my region. Question? Nope. All right. Antiderivatives. Antiderivative of 4 is, or we could say 4 is the derivative of 4x. Oh yeah, and undoing the power rule. So I had x squared, increase the exponent by 1, divided by that new exponent. There's my area function. Good. But I know that when x is 1, my area is 0. So I have 4 minus 1/3 plus c. 4 is 12/3 minus 1/3, 11/3. So c is negative 11/3. So now I know a of x is equal to 4x minus 1/3 x squared minus 11/3. Oh, x cubed. What is a of x? It's my area under the curve from 1 to x. I want to know from 1 to 2. So I want to find what is a of 2. Eight minus 11. 19/3. Should change this already, you say? So the area is 1 2/3 or 5/3. So let's just look back at this. If you think about how much area we have, if this were a straight line there, then this area here would be the same as that area there, right? If it were linear, but it's not quite. So there's a little bit more area here because it curves out than there is over there. So if I add that piece to this piece, it's going to be a little bit bigger than 1. Plus I have this middle part here, which would have been a half if this were a straight line, but it's not a half. It's a little bit bigger than a half. So if we reason it through, we could say, yeah, it makes sense that it's bigger than 1, less than 2, probably closer to 2 than it is to 1, which fits our answer. You don't have to be able to visualize that, but I just thought, let's try to convince ourselves that this is a reasonable answer. There we go. We can find area under curves. Questions on this one? Okay. We want to determine the area under this curve. We start at the same place by defining our area function. A of x is going to be the area under this curve from 0 to x, which means a of 0 equals 0. In other words, if there's 0 width, there's 0 area. And we're going to want to figure out what's that area there. Rayon? Well, we're going to move past this to some other notation that we will tend to use more than this. What's next? Oh, Ajay? Now what do I do? Oscar, what do I do? Yeah. So figure out what's my area function going to be. The integral or antiderivative of 3 secant x tan x dx. Notice, I've taken the 3 out in front of my integral sign because it has no x's with it. So again, if I have some constant that's multiplied, I can factor that constant out in front of my infinite sum. Secant x tan x is the derivative of what? Tanuri, did you say? No? Balraj? You might have. What might you have said? Yeah, this one's not on the formula sheet. Oh, is this one on the oh, maybe it is there. Oh, what's it equal to? Secant x plus c. Figure out the c value. In the nicest sort of way. No comment.
Yeah. What's the R of this?
So equals, I mean, C equals negative 3, right? What's called height? 1/2.
That's cool. We're looking at
-1. -1 is negative. sub x plus c.
Yeah. C looks like C. So then A.
And then so you have 3, so you have 2 minus 3. Minus 3. No, minus.
That's 3 times 3. 9. You know, please.
We have 3 times 2 minus 3 times 3. Yeah, so it'd be negative 2. How many weeks like that?
He has what I have.
Secant of pi by 3 is what?
Why do you rock around this
2. 3 times 2,
6,
6 minus 3.
5? Wait,
Nice try. Oh. So, question was asked, why don't I have a 3 there? Because if I'm doing the antiderivative of this, it is secant x plus c, and all of that had the 3 multiplied in front, right? So c is representing what? A constant, just a number. So 3 times a number, still just a number. So we ignore any number that would be multiplied to it because it's still just a number. So it doesn't matter. So that's why we end up ignoring the fact that that is multiplied by 3, but that's just part of the mystery of what C is. It's just a constant anyhow. Okay, so we won't bother putting that 3 in there. And then you can try number 5. But first, man. Oh, then here, if we were looking for the distance between 1 and pi over 3, which would work, because pi is 3.14, so that'd be some value over here. At this point, we would have said a of 1 equals 0. And that would have given us a different constant here. So we would have a different constant, so our function would look a little bit different because the constant would be different.
Just 2 squares, yes. Oh yeah. So